So we continue with the example. Okay. So now we go to the complete question. Complete question for the pole placement. Okay. The question is, the example is, write the question. Example. Example number 3. Okay. Design the system. Okay. That yield at positive overshoot equal to 9.48% and the TS equal to 0.74 second, where the system is equal to 20s plus 100 divided by s cubed plus 5s squared plus with the 4s. Okay. Alright. So this is the system. Okay. So according to the previous slide, I show you we need to focus on two parts. Okay. So this is the first part for the uncomposited. And then we need to focus on the second part for the compensated system. Alright. So in this case, every part, I show you there are a few steps. Step number 1, step number 2, step number 3, and step number 4. Okay. And then after that, I also inform you that the source or the start point to solve the first part uncomposited is starting from the transfer function gx, or the question 20s plus 100 divided by s cubed plus 5s squared plus with the 4s. And then I also inform you that in order to solve for the second part, we need to start the compensated system. We need to start with whatever information of the transient response. In this question, the information that we need to have is percentage overshoot equal to 9.48%, and also the setting time is 7.04 seconds. And then after that, we need to calculate the damping ratio and also the natural frequency. Okay, so this is our main reference before we can solve this kind of the question or design the controller. So now we need to focus on the first part lah. We need to focus on the first part uncomposited system. Solve for the uncompensated system part first. Okay, so I need to look at the step that I developed. Okay, firstly, before we go to this part, we need to check or convert the system to the phase variable form and controllability. We already did these two process done, and the system is controllable. So now we can proceed to solve the question. Okay, firstly, we need to find, step number 1, we need to inject or replace u equal to minus kx, and finally we get the new state space a minus bk x. Okay, done lah. Step number 2. Okay, so we need to calculate lah a minus bk. A minus bk. According to our previous answer, our A matrix is 0, 1, 0, 0, 0, 1, 0 minus 4 minus 5. Okay, and then our B matrix is 0, 0, 1, and our K matrix. What is our K matrix? Anyone? Our K matrix should be in our K matrix. How many K that we need to use? Murad?
3.
So we should name as for the K matrix. Murad? For the K matrix here, we should name as
K1, K2, K3.
K1, K2, K3. Okay. This is very straightforward. So now we need to find our A minus BK lah. Okay, because this is our new A. So we need to solve this one. So the A minus BK actually 0, 1, 0, 0, 0, 1, 0 minus 4 minus 5 minus with B multiply with the K. K1, K2, K3. Okay. So we need to go to the next page lah. So after that, we get A minus BK equal to 0, 1, 0, 0, 0, 1, 0, minus 4 minus 5, minus 4 minus 5. Okay. I need to confirm this is my A, that's correct. Okay, minus 0, 0, 0, 0, 0, 0, negative K1, negative K2, negative K3. This is what happens when you multiply matrix B and K. And finally, this is your A minus BK is 0, 1, 0, 0, 0, 1. This will be K1. Should be negative 4 plus K2, and then should be sorry, I need to, okay, this supposed to be K1, K2, K3, because that's why I feel something wrong here. When you multiply this one, you only get K1, K2, K3, okay, and then after that you will get for the A minus BK, this is negative K1, it should be negative K2 plus 4, and here will be negative K3 plus with 5. This is A minus BK. Then we go to step number 2. We need to find the characteristic equation. So we need to find or get the determinant Si minus the new A. This is the new A. Okay. Si minus the new A. So firstly, we need to find Si minus the new A. So we have Si, this is your Si. And this is the new A. 0, 1, 0, 0, 0, 1, negative K1, negative K2 plus 4, negative K3 plus 5. And finally, this is your Si minus the new A is S negative 1, 0, 0 S negative 1. This will be K1. Should be K2 plus 4. and this one is S plus K3 plus with 5. This is your Si minus A, the new A. And finally, you need to calculate the determinant of Si minus the new A. So as usual, you just choose any row you like or column you like. In this case, I want to choose the top one. So I just put it here as -1 for the 0. Okay. And then after that, I need to close. I will get as -1 K2 plus 4, and here will be S plus K3 plus with 5. Okay. For the negative one, I will get 0. Okay, 0, -1. To close it. 0, -1, and then K1, S plus K3 plus 5. For the 0 part, I don't care lah, because just multiply the 0. And then after that, I apply the sign, positive and negative. And finally, I get the determinant as I minus the new A is. I solve it. Finally, I get S cube. And then after that, K3 plus 5 plus with K3 plus 5 S square plus with K2 plus 4S. Okay, and then after that, plus with K1. So this is the second step. Alright. Okay. So now, done for the uncompensated part. So done. This is done. Okay. So next, we go to the second part here. Okay, I need to share this one. Share screen. Share now. Okay, we already done at this part. We already done A minus BK, and then after that we already done find the determinant as I minus A minus BK. Done. Okay, and then after that, before we need to compare the CEB required system, so we need to solve the composited part system for the step number 1 and step number 2. Okay, so our design criteria from the question say that, so we go to the compensated system, the second part, or the desired what you want. We want the system change to 0% overshoot equal to 9.48%, and then the setting time equal to 0.74 seconds. Okay, if you still remember, the formula for the percentage overshoot is,
Doctor,
yep,
blank screen.
alright. Saya tukar je. Thank you. Cancel. Share screen. Start sharing. Okay, so we go to the second compensated system for our desired. Firstly, the percentage overshoot they want is 9.48%, and the setting time is 0.74%. And this is the formula that you must remember. If you still remember that, if you want to calculate the damping ratio based on the percentage overshoot, you need to use this formula. Okay, this is from control number one. Okay, according to what I would calculate, the value of the damping ratio is 0.6. Okay, and then after that, in order to get the omega n or natural frequency here, so because our target to find the damping ratio n natural frequency, the omega n based on the setting time Ts equal to 4 over zeta omega n. This is the formula that you must know. Then after that, your omega n equal to 4 divided by 0.74 multiplied with 0.6. Finally, your omega n is 9 radian per second. Okay, so now you have these two formula. Theta equal to this information 0.6, and then omega n equal to 9 radian per second. Okay, according to the table, after you have this information, you must apply to the characteristic equation formula for the second order system, which is s square plus 2 zeta omega ns plus with omega n square. So you just replace everything, all the values you have. Finally, you get the characteristic equation is s square plus 10.8s plus with 81. This is your characteristic equation for the desired system. Okay, so both of the composited and uncomposited system, we already done for the step number one and step number two. So now it's time for us to put all the information side by side at step number three. Step number three, yeah. So we have the question is GS equal to 20 s plus 5. Okay, the question s cube plus with, what is the question again? I need to see. 5s squared plus 4s. So the characteristic equation, when you apply the pole placement, you obtain k3 plus 5, k2 plus 4. Okay, you obtain s cube plus k3 plus 5 s squared plus k2 plus 4 s plus with k1. Okay, and then after that, based on the information you have, percentage overshoot equal to 9.48% and setting time equal to 0.74 seconds. Finally, you get the characteristic equation is s squared plus 10.8s plus with 81. Okay. In this case, I want to ask you, then we need to compare with these two. Because according to step number three, we need to compare the characteristic equation of the uncompensated system with the compensated system. So I want to ask you, is it these two characteristic equation can be compared? Is it can be compared or not?
Yes.
Once again, what is the
Yes.
answer?
Because
Yes.
S
Why?
square S and K1, we can get the value.
Okay. All right. Good try. Uh, the answer is cannot be compared. Okay. So anyone would like to tell me why these two characteristic equation cannot be compared?
Different order of system.
Yeah. Yes, because different order of the system. Because this is state order of system, and then this is second order system. Cannot. You just can compare the system with the same order only. Alright. So what do you think we need to do? What is the solution that we can do? Anyone? In order to compare, we must to make sure both of the characteristic equation must have the same order. Is it? So what we can do in order to make sure the system have the similar order? Okay, anyone? Do you have any idea? The clue at this part. So what we need to do to this system? We need to make it, the system become what?
Third order.
Yeah, we need to change this system from second order to the third order. So how we want to do that? So we just take the second order, the characteristic equation here, s squared plus with 10.8 s plus with 81. So we need to multiply with another pole. Okay, because this contribution two poles. Right, because second order two poles lah. So we need to add another pole to this characteristic equation in order for us to do the comparison. So what is the pole location? Okay. So in order to determine the pole location, we need to refer the zero location here. Zero location. Okay. We have the zero location is s power of 5. S power of 5. So we just choose any pole that have this value of the zero from the uncompensated system. Why we do that? Okay, I tell you that. Yeah, I need to on my laptop again because it locked up. Because this characteristic equation that contribute to 9.48% overshoot and setting time 0.74 second. If we add another pole here, okay, so it means that our percentage overshoot and setting time will be changed. Okay, it will be not the same because only this value can make the percentage overshoot equal to 9.48% and cycle time equal to 0.4 seconds. If we add another value, automatically we cannot get 0% overshoot 9.48 and cycle time 0.4 seconds. So that's why we choose the third pole equal to the 0 because s plus 5. However, we cannot choose the exact value. We need to choose some change value such as s plus 5.1 or s plus 5.001, anything as long as not at the same value. Why is that? Okay, because from the uncompensated system, we just change the characteristic equation, kan? And then for the compensated system, we just change the uncompensated the characteristic equation only. However, the the poles for uncompensated system and compensated system will stay the same, will be the same. So it means that if the post location will be the same, so let's say this is our new characteristic equation, kan? S plus kita tadi 10.8 S plus 81 S plus 5.1. This is our third pole. Because the post location at the site still the same, so it means that this is 20 S plus 5. This is GS. With the of the uncompensated system, this is the GS of the compensated system divided by S cube plus B K3 plus 5, K3 plus 5S plus K2 plus 4S plus K1, and this is the composited system. The top or the pole location still the same, S plus 5. So it means that uh, why we choose this value? Because we can cancel out. If we can cancel out, so it means that at the end we will have the same characteristic equation that contribute to the 9.48% of the percentage overshoot and the same setting time 0.74 seconds. However, we cannot choose the exact value because it can totally cancel out. However, we just want to have a very slightly different because we cannot remove the zero from the original location. However, we can something like virtually eliminate the zero by implementing the pole that almost have the same value of the zero. Okay, so now we have s cubed plus k3 plus 5s plus k2 plus 4 plus k1, and this is our new characteristic. After we multiply together equal to 0, we have s cubed plus v. What is the answer again? 15.9. 15.9 s cubed plus v 136.28 s plus v 413.1 equal to 0. Alright. So finally we go to step number 4. Can anyone tell me what is the value of the K1? What is the value of the K2 and value of the K3? Can anyone tell me or calculate for me? The K1 value equal to this supposed to be S square, this is S. We need to compare. We can compare because this is the third order system. This is where S power of 2, this is S power of 2, S power of 1, S power of 1, and this is S power of 0, S power of 0. So what is our K1 value?
413.1.
413.1. What is our K2 value?
13208.
Okay. K2 value? Boleh congak ya?
13208.
132.08, and our K3 value. Boleh congak juga.
10.9.
10.9, that's correct. Alright. So at the end, you can draw again the signal flow graph. Okay. The signal flow graph. Kita nak lukis balik lah. Okay. The signal flow graph, the system without the pole placement controller. This is what you need to do lah during the lab number 2. Okay, during the lab number 2, this is the signal flow graph for number 1, the uncomposited. And this is the signal flow graph for number 2 for the compensated. Okay, we need to find the difference. As I say to you, you need to start from U, from the output. Okay, and then this is what we have already drawn before at the beginning of the class. We have 1 over S, 1 over S, 1 over S, because this is state of the system. We have 3, 1 over S. Ini saya kena lukis sikit. I need to draw a little bit low. U and Y. Okay, we draw a line there. This is 1 over S first. This is the second 1 over S. And this is the third 1 over S. Right? And then after that, we need to label. This is X1, X1 dot, X2, X2 dot, X3, X3 dot. Okay. After that, according to this one, again here will be 1, 1. Okay. And after that, we get for the X3 dot actually is coming from negative 5x3 and negative 4x2, okay, and plus with 1 multiplied with u. And then for the output y, we have 100 x1 plus with 20x2, 20x2. Okay, this is the original system now. So after that, when we apply the pole placement controller, we just need to add the feedback gain. K1 actually coming from X1, negative K1. And then the K2 from X2 will be negative K2. And then K3 from X3 go to here, negative K3. However, from the calculation, we calculate that our K1 equal to 413.1, and then our K2 132.08, and then our K3 is equal to negative 10.9. So when you want to run your simulation using Simulink, you need to come up with signal flow graph first. Okay, you must come up with the signal flow graph first, and then after that, you can run the simulation using the Simulink. So this is how you connect all your integrators, your input step, your output scope, everything in the MATLAB Simulink in order to solve for the lab number 2. All right. I think for the pole placement controller implementation, you just need to remember the step. That's really important. If you understand the step, because the step already gives to you, okay, I already give you the step. Okay, I already give you the step. However, you just need to know how to use this step in order to to design the pole placement controller. Okay. So the next video I will upload about the observable controller. However, the observable controller, the steps are same to the pole placement controller. However, the difference between the pole placement controller and observable controller, the only part, not the only part, the different parts between these two is mana dah? Okay. In this case, for the pole placement, you need to replace U equal to minus KX. However, the pole placement, you need to replace U equal to something else. U equal to LC, something like that lah. Okay. And then after that, for the pole placement, you need to convert your system to the phase variable form. However, for the controller, you need to convert your transfer function to the OCF. After that, the rest of the steps are same. So it means that if you understand the pole placement controller, you can do to design the controller for the observable controller. Okay, so this is the main thing that you must refer lah during the exam, because you have the open book exam. You just need to have this table in order to solve the question, and then after that you need to understand every step that I mentioned. Oh, I didn't share my screen. That's why share. Okay. So I would like to tell you again, explain again. This table is really important. Okay. You just need to know what you need to do lah, or the flow you must follow in order to solve this question, because during the open book exam you can open this table, you can refer to this table in order to design the pole placement or the OCF or the controllable controller. As long as you understand every steps here, you are okay. You can design both controllers easily. Okay. And I'd like to mention you again, the only difference between, not the only difference, the difference between the pole placement controller and observable controller. Mana dah? Okay, for the pole placement, you need to refer or replace U equal to minus KX. However, for the pole placement, you need to replace U equal to LC, something like that. Okay, and then after that, for the pole placement, you need to convert your system to phase variable form. However, for the observable controller, you just need to replace your transfer function to the observable canonical form. The rest of the steps, if you refer to this, are same. Okay, are same. Everything same. Okay. All right. I think that's all for the pole placement controller. Okay. I hope you understand, not fully understand. I hope you grab the main idea for this lecture only. The main idea also okay, no problem. However, please do again this exercise. Okay, please do again this exercise in order to help you to design the pole placement controller, not only during the open book exam, but for the lab 2, because I plan to conduct your lab 2 on next week. You will have your lab 2 on next week. So on next Thursday, you are welcome to go to the lab in order to do your lab 2. Okay, so I will upload the lab 2 module around Monday, something like that, for your preparation before you go to the lab. All right, I think that's all for the pole placement controller and our last online class. After that, we will meet again another next week. After that, that's all lah for this semester. My class with you all. And then we have our test one on this coming Monday, Monday night. So as usual, if you have any question, please, I will wait another 5 to 10 minutes to answer your question. Let's say if you did not have any question, please help me to fill up the attendance form in the chat box. If you didn't have anything, so you can leave the meeting. That's all from me. And Assalamualaikum, and see you on next week during the test and lecture. All right, guys. Okay, guys. I need to stop the recording. Stop recording.
Thank you, Doctor.